Well, hello everybody, and welcome to Chem, and we are discussing thermal chemistry, right? And last time we talked about delta H, and I want to get back to delta H for a second and add some meat to this, right? So we were over here and we said we were talking about delta H, and we said delta H was what? That's change in enthalpy. Cool, right? And we said, hey, delta H is equal to Q at constant pressure. Okay, good. So that means change in enthalpy is equal to the heat transferred if our process is at constant temperature. And we started talking, and I really didn't quite say this, but about something called delta H reaction. And what is delta H reaction? Well, that's going to be the H of my products minus the H or enthalpy of my reactants, right? Good. And we kind of talked about this earlier. When my delta H of reactants is less than 0, that means what? My reactants have more energy than my products. That means that's an exothermic reaction, and that means Q is lost from the reaction, and we're going to say that our reaction, right, is going to be our system, and so everything else is the surroundings, right? So here are the surroundings. Here is my system. If Q is lost by my system, then Q is a negative. Good. And we also talked about another thing too. What could be done? I can actually do some W by my reaction, and that is work, right? And typical work for chemistry would be P delta V, and if it's work done by the system, it's a negative P delta V, right? When work is done by the system, it's negative. When heat is leaving the system, it is negative, right? Cool. Now, I also could have a situation where my delta H reaction is greater than 0. That means that my products have more energy than my reactants, which means energy went into the system, so it's endothermic, which means Q is positive, right? Okay, cool. And we talked a little bit about delta H, that if I have, what did we have yesterday? 2H2 plus O2 going to 2H2O, and my delta heat, my delta H of reaction was, what was it? Let's see, not there. How about right there? How about right there? Negative 484, we'll call it, okay? Negative 484. Zoink, where am I? I'm lost. Negative 484. Yoink, yoink, there we go. We said that this is equal to negative 484 approximately to 3 sig figs. So we said that delta H, we have to be careful. Delta H is extensive, meaning the number of moles matters, the amount matters. So if I only have 1H plus 1 half O2 going to 1 H2O, it would not be negative 484. In fact, since the moles of hydrogen and the moles of oxygen are cut in half, this would be, for this specific reaction, delta H would be a negative 242 kilojoules. And if I didn't have a mole, if I only had 5 grams, then I'd have to convert those grams to moles and then look at the ratio, right? We'd say, based on this, there are negative 484 kilojoules per 2 moles of H2O. So if I only had 5 grams of H2O, what do I have to do? I have to convert the 5 grams of H2O to moles of H2O and then multiply by this ratio, correct? Great. And we also said direction matters, that if I have 2 H2O going to 2H2 plus O2, that is the exact opposite of this reaction. So if I go from hydrogen reacting with oxygen and it is exothermic, then when my water goes to form hydrogen oxygen, it's going to be endothermic, but since it's 2 moles, it's the same quantity, right? 484 kilojoules. Cool. And we want to go farther now today with that concept. So let's look at this. Consider carbon plus oxygen going to form carbon dioxide. Okay, and I have some information here about the heat of reaction. And I have carbon monoxide reacting with some oxygen, and it'll form carbon dioxide. And I have another heat of reaction. Now the question is, what do I have for a heat of reaction when carbon reacts with oxygen to make carbon monoxide? Now, when I analyze this, do either of these make carbon monoxide? The answer is no. Here's what I do see. I see carbon monoxide here, right? Okay. It's on the wrong side, so I want to rewrite this and put it on the right side. So I'm going to go CO2 gas. We always have to watch our units, right? I mean our states, correct? And that's going to go to CO gas plus 1/2 O2 gas. Okay, great. Well, so now I have CO here and I have CO here. But now, how does the rest of this look? Well, it doesn't look very good because I have a carbon here and I have 1/2 oxygen. And I have to get rid of this oxygen here. Well, when I add this to it, it's carbon plus 1 oxygen gas is going to CO2. What happens when I combine these two? Well, I would get CO2. I'm going to write everything on the left side of the arrows together. CO2 plus C solid plus O2 gas yields CO gas plus 1/2 O2 gas plus CO2 gas, right? But can I simplify this? Well, I have CO2 gas on both sides, and it's 1 mole of each, so I can cancel those. I have 1/2 oxygen on this side, and I have what? 1 oxygen on this side, so what do I have when I have 1/2 on one and 1 on the other? Then this is eliminated and this becomes 1/2. So I have C carbon plus 1/2 O2 gas yields CO gas, right? Is that what I'm looking for? Hey, that's exactly what I'm looking for. So what I've done is I've taken 2 steps. This would be step 1, and this is step 2, and I added them together to get my final equation. Well, we can do some stuff with delta H using that idea. And so let's add some notes here. Zoink, 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 zoink. There we go. Notes. We want to add something called Hess's law. And we might want to come off of our discussion of delta H here. So coming off of delta H, yikes. I didn't even put a circle for delta H. Here, delta H, let's come off of delta H because we want to talk about Hess's law. Hess's law. And what Hess's law says that if a reaction can be presented or represented as a series of steps, then delta H for the reaction is the sum of delta H for each step. Got it? That's pretty simple. So if I have something like this, and I said I'm going to take the first, let's go back and talk about what I did. I have step 1 and I have step 2. I'm going to add them together to get my final. That means if I take delta H1 plus delta H2, it should equal my delta H3. So what's delta H1? Well, delta H1, what's my first step? It's CO2 going to CO plus 1/2 O2. Well, do I have that? Not exactly. I have what? CO gas plus 1/2 oxygen going to CO2. Well, this is the opposite, isn't it? Right here is the opposite. So what do we have to do? Well, we're going to have to take delta H and change the sign. So my delta H here is 283.0 kilojoules. You guys see that subtlety? Step 2 is exactly the same as this. So that means my delta H is negative 393.5 kilojoules. So my delta H for the total reaction are these two things added together. So I'm going to take what? 283 plus negative 393.5, and my answer is not that. 393.5, how about 111 when I round it? 111 kilojoules, and that is what? Negative. Zoink. Negative 111 kilojoules. You think you guys can do that? Well, give this a shot. Bring me back when you're ready. Ooh, this looks complicated, doesn't it? It looks like a lot of stuff. Well, this is a lot like making a puzzle, and I love puzzles. So let's see. I need to have C2H2 on this side. You see any C2H2? Yeah, I see C2H2 right here, but it's on the wrong side. So what are we going to do? Well, excuse me, this is the one we want. Yoink, that's my final. So I want C2H2 on my product side. So what I'm going to do with this guy here, I'm going to flip that reaction. So I'm going to say 2CO2 gas plus H2O liquid yields what? C2H2 gas plus 5 halves O2 gas. And now, what's my delta H for that? Well, since I flipped it, I have to change the sign. So it's 1299.6 kilojoules. Got it? So that we'll call that step one. Step one. Now, what else do I need? I need to have 2 carbons on this side. Well, I only have 1 carbon here, and it's the only place I have single carbons, right? So what do I need to do? I need to double that. So I have to multiply this by 2. So that means I have now, step 2 will be I have 2 carbons plus 2 oxygens, and they are, we better watch what's my state here, gas, yields 2 carbon dioxide gases. And what's my delta H for this step? Well, I had to do what? I had to double that, so I need to multiply this number by 2. And so what do? We take 393.5 negative, oh yes, I got that, times 2. It looks to me like a negative 787.0 kilojoules. 787.0 kilojoules for step 2. So that's 1, this is 2. Now, does this work out? Am I done? Well, let's see. My 2 carbon dioxides will cancel, right? This guy will cancel here with this guy. I still have too many oxygens, and I have this water, so I need to get rid of this I need to get rid of this water. So that means I need water on the other side. I need to get this hydrogen, and here's okay, so I'm going to add this guy right here. So step 3, this is step 2. Step 3 is going to be what? Well, it's going to be H2 gas plus 1/2 O2 gas yields H2O liquid, and my delta H did what? It stayed the same. Delta H step 3 is equal to negative 285.8 kilojoules. Now, if I'm a good puzzle maker and I add these all up, I will get what I want. So first of all, I have 2 carbon dioxides right here. There's 1, and here's 1, so they cancel. What else? Anything else? I have an H2O here, zoink, and an H2O here. They're the same. They're both liquids, so they'll cancel. What else do I have? Well, I have 2 carbon, right? And I have 2.5 oxygens, and 2.5 oxygens are equal to what? 5 halves oxygen, so my oxygens cancel. And so I have 2 carbons plus H2 gas yields C2H2 gas, right? Is that what we're looking for? Hey, that's exactly what we're looking for. Yahoo! So all we have to do then is add these 3 bad boys. And let's do that. I have a 1299.6, which is positive, right? Let's see, positive. Let's make sure. Yes, that was a negative, and I switched it around, so that's a positive. And from that, I'm going to subtract 787, and I'm going to subtract 285.8, and my answer is 226.8, and it is a positive, and so my delta H for the reaction is 226.8 kilojoules. Great. Excellent. Okay, perfect. Let's see, how are we doing on time? Oh, we can finish this off. Great. Okay, so that was Hess's law. Now we want to get into a specific type of problem called a coffee cup calorimeter. And believe it or not, you really need to know this stuff. It will show up even in things like AP tests. So what's a coffee cup calorimeter? We have a coffee cup calorimeter containing 50 milliliters of 1 molar hydrochloric acid, and we have 50 mils of 1 molar sodium hydroxide. Okay, I have a thermometer in there, and I see that the temperature changes, and they want to know what is my delta H of reaction. Okay, we need to go back to notes. And where are my notes? Oh my gosh, I've lost my notes. Okay, we're going to start with a new page. Underneath our delta H, right? We've talked about kind of my definition of what delta H is. And here we really want to talk about determining delta H of a reaction, right? We have our delta H of reaction. We talk about Hess's law, just trying to fill in the concept map. And now we want to talk about determining delta H of reaction. And one way to do that is called calorimetry. And we want to talk about a subset of calorimetry called coffee cup calorimetry. Okay, and in coffee cup calorimetry, really what you have is a coffee cup. All right, it may be a little more advanced than that, but essentially it's a coffee cup. It's an insulated container, such as a styrofoam coffee cup or a couple styrofoam coffee cups. And you usually have a solution, and then a reaction takes place in this solution, right? Well, where does all the heat from that reaction go? All the heat from the reaction goes into the solution. And then if I can take the temperature of the solution and I can figure out the Q of solution, that means all the Q of the solution came from Q of my reaction, right? And then from that I can figure out my heat of reaction. So that's kind of what we do. We put a nice insulated top on it, put a thermometer in it, we let the reaction occur inside the coffee cup, and then from that we can determine the delta H reaction. Now here's the process. Number one, we want to first figure out what is my heat gained or lost by my solution. By the solution, not the reaction, the solution. Well, we're going to use one of our old friends. Q equals MC sub P delta T. We're going to say the Q of my solution equals the mass of my solution. Now remember, this is of the solution. So mass of my solution is going to be equal to what? Well, it's going to be mass of my solute plus mass of my solvent, right? We're looking at the total mass. So mass of my solution times my my specific heat of the solution times the delta T of the solution. Got it? Okay, that's easy. We can do that. We're experts at that. Now, the second thing has to do with what? The first law of thermodynamics, right? Energy is neither created nor destroyed. So, where did all that heat of the solution go? Or where did it come from, actually? Well, all the heat of the solution came from what? Heat of my reaction. The reaction occurred, it either created or used heat. That heat went into or came out of the solution, so the magnitudes are the same, and the only difference is the signs. If my reaction has a positive heat, then my solution has a negative heat, right? Because that would mean heat is lost. Let's go with red because it looks like heat, right? Heat is lost by my reaction, which means it's gained by my solution. Cool. Well, that's easy. We can do that. And in fact, we've done questions similar to that, right? And then finally, though, delta H for my reaction is going to be Q of my reaction per, usually, mole of a reactant. So you'd have to figure out how many moles of the specific reactant were used to create this amount of heat, and then you divide it into the Q reaction. And this is going to be they're going to tell you in the question moles of which reactant. But that's all there is to it. It's really quite a simple process. It's much harder to do in reality, but it's not that difficult of a thing. Let's see, here we go. Let's see if we can do it. Coffee cup calorimeter. Okay, so I have a coffee cup here. What's going on? I have NaOH, yoink, and I have HCl, and when those two guys react, they are going to create heat. They're going to create water and a salt and heat. So this reaction occurs, and it's going to create some heat. And where will that heat go? That heat will go into the solution. And we're going to measure the temperature of that solution, right? And what do we know? The temperature of the solution goes from, it increases, so Ti is equal to 21.0, and Tf is equal to 27.5 degrees Celsius, okay? So we know that. How much stuff do we have? We have 50 milliliters and another 50 milliliters. Okay, and it says the volumes are additive. And what else do we know? It says the solution has a, what's that thing? That is a rho. And that is the physics way and math way of saying density, right? Chemists tend to use D, engineers like I am tend to use rho. And so we know that the density of the solution is 1 gram per milliliter. So let's start working on this. I need to get mass of my solution. I don't have mass, I have volume, right? I have 50 milliliters of, how many sig figs do I have? 50 milliliters of HCl plus 50 milliliters of NaOH. So what is my total volume? Well, it's 100 milliliters of solution. My whole solution is composed of just the HCl and the NaOH. So I have 100 milliliters of solution. Now, how do I get mass of my solution? Well, it's going to be 100 milliliters times what? Well, they give me the density. Hey, I can handle that. 1.0 grams per milliliter. I can do this without a calculator. I have 100. There's only 2 sig figs now because there's only 2 sig figs. I have 100 grams, and that's not significant there, 100 grams of solution. Okay, cool. So I know what my grams are. It says what? The C sub P, ooh, you know, there's a problem with me writing everywhere. I cover up some important stuff. My C sub P for the solution they give me is 4.18. Okay, so what do we want to do? We want to get Q of the solution. So Q solution is mass solution, C sub P solution, delta T solution. Good. What's mass of solution? Hey, we know that is 100 grams, 2 sig figs, times what? 4.18 joules per gram Kelvin, times, I have a delta T. Yeah, sure, I have a delta T. TF is 27.5. Remember, delta T is always TF minus TI. That delta T can sometimes be negative, right? Cool. There we go. And so when I do this subtraction here, I get 6.5, so I'm down to 2 sig figs there, right? Let's run our numbers. Zoink. What do I have? 100 times 4.18 times 6.5. So that means Q solution is equal to 2717 kilojoules. Got it? Excellent. Let's make sure I ran those numbers right. 27.5, yes, 6.5, 650, 650 times 4.18. Yeah, there we go. So that's right. So that's my Q solution. But we're not really interested in Q solution. We're interested in Q reaction. Well, where did all this heat come from? Well, all the heat that the solution got, yoink, came from where? came from my reaction. So Q reaction equals Q solution, but the reaction lost it and the solution gained it, so the difference is a sign. So what is my Q reaction? A negative 2717 kilojoules. Cool. There we go. Is that our answer? Not quite, because what do they want? Let's erase so we can see stuff. They want it in terms of kilojoules per moles of HCl. What do I have it in? I have it in just kilojoules. So what do I have to do? I have to take that number and divide it by moles of HCl. Well, how do I get moles of HCl? We need to get moles of HCl. Well, moles of HCl is going to be liters of HCl times the molarity. How many liters did I have? I had 50 milliliters, which is 0.050 liters. What was the molarity? 1.0. Zoink, right there. 1.0. 1.0 molar. And so what do I get? It looks to me like I have 0.050 moles of HCl. So what is my delta H reaction? Well, it's going to be my Q reaction, which is a negative 2712 kilojoules divided by my moles, 0.050 moles of HCl. And when I use the wonders of my microchips, I end up getting boink what? 0.050, and it looks to me like I get 5, 4, 3, 4, 0. Oops, I made a mistake. Where was my mistake, ladies and gentlemen? Right here. Look at that. This is not kilojoules. This should be joules. And so that should be joules, which means that this is joules, which means this is 54340 joules per mole Kelvin. And I have to watch out. You don't want to lose your sign. And so I have to divide that by 1,000. Yoink, yoink, yoink. And my answer is 54, 3 sig figs, right? Kilojoules per mole of HCl. Woohoo! Negative, negative, negative. There we go. I got to have that negative. Negative 54, meaning when my hydrochloric acid reacts with my sodium hydroxide, heat is released. You do the last one, and we're done for the day. Well, what do we have here? Coffee cup calorimeter. That means we're going to go with Q of solution equals M solution, C sub P solution, delta T solution. And then we're going to say that that is all equal to negative Q reaction. And then I'm going to divide that Q reaction by moles of something. And what do I want this time? I want moles of silver nitrate, and that's what we're going to do. So first thing, what is my mass of solution? Well, my solution is made out of what? Silver nitrate and hydrochloric acid. So what do I have here? I have 50 mils. Looks like I can't go directly to volumes. I have to go with volume. I mean, can't go directly to mass. Let's go with volume first. I have 50 milliliters of silver nitrate plus what? 50 milliliters of HCl. So I have 100 milliliters and 100.0 milliliters. Do they tell me a density? Oh, yeah, I didn't have to do that. They tell me that it's 100 grams. Doink. Says that the assumed mass is 100 grams. You know, if you read the entire problem, sometimes you get good information. Excellent. So I didn't even have to do the volume. Silly me. Now, what happens to temp? Temp increases from 22.3, so TI is 22.30. TF is what? 23.11. So we have everything we need, because here is my C sub P. Q solution is equal to 100.0 grams times 4.18 joules per gram Kelvin. I'm not going to make that mistake again. Delta T, 23.11 minus 22.30. Excellent. Let's run the numbers. 100, zoink, 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 zoink. Oops, I had 1,000. I'm going to start over here. 23.11 minus 22.30, and I get 0.81. So I'm down to 2 sig figs there. 0.81 times 100 times 4.18, and I get 338.5. Now I only have 2 sig figs. This is joules, right? Let's run those numbers again. 100 times 4.18 times the quantity, 23.11 minus 22.3, zoink, zoink. Looks good to me. So this is my Q solution. It's a positive number. What is Q reaction? Well, it's going to be opposite of Q solution. So it's going to be negative 338.5 joules, right? Now, I want it in terms of moles of silver nitrate. So how many moles of AgNO3 do I have? Well, I'm going to take the volume of my AgNO3 in this case. I have 50 mils, 0.050 liters, times what is it is a 0.1 molar, 0.100 molar. And so what do I get out of that? How about a 0.005 I think there's another O there, moles of AgNO3, right? That looks good to me. And then what is my delta H reaction? Well, it's going to be negative 338.5 joules divided by 0.00500 moles of AgNO3. And so what do I get out of that? Divide that by 0.005, and I get 67716. That is a negative value. That is joules per mole of AgNO3. I only have 2 sig figs, right, out of this. So that means this has to become negative 68000 joules per mole. But I don't want joules, I want kilojoules, so that means we need to go yoink, 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 and that is a negative 68 kilojoules per mole of silver nitrate. Woohoo! That's not so bad, is it? Okay, ladies and gentlemen, that should do it for the day. I went a little long, but it's good stuff. See you next time. Bye.